That is kind of a long introduction to the class to get started for today. And so let's go ahead and get started here into chapter 11. Last time we met on Wednesday, I said we would get started in chapter 11, and instead I did an extra number of examples from chapter 10. It was kind of a decision I made on the fly, thinking that would be useful to you in the sense that you know, the more examples you can see, the better, which is always a good thing. Oh, I know the last announcement I was going to make is, and I should have picked Don's brain, but on Wednesday, we'll put on the board here, since you guys have the test coming up, he's going to want to do a review. And in the past, he's done it on Sunday. I suspect he'll probably want to do it on Sunday again for you guys. It's a good time. Although, since your test is on Wednesday, Monday night, oh, there's a math classes on Monday night. There are. And I think Don prefers Sunday anyways. He prefers the 2 days in advance. Not one day he thinks is too short, and 3 days is sometimes too early for people to get a good review. So I know he prefers the 2 days. So I'll have to check with him what he prefers. But I know he prefers the Sunday afternoon. He says he feels more refreshed than at the end of the day on a Monday night after going through class and going through work and all that stuff, and then trying to come in for a 2-hour review with you guys. So most likely Sunday, and I'll check with him, or we'll check with him when we're in lab today. Okay, well, maybe I'll jump back over here, because on the board for these last couple of lectures, I've always kind of put a little chart here and said, all right, we should look at our translational motion and we should look at our rotational motion. And we've had a long list, and we went through a lot of examples on Wednesday, and that would be a good YouTube one to watch again as we get ready for the test and say, okay, how do you do these problems, or how do you do the homework? But there was one thing, and you guys pointed it out, the one connection between these first 9 chapters that we did for translational, we haven't done for rotational. What was it again? Yeah, momentum. And so we had momentum, and we just called it momentum, but now we should be more clear. Let's call it angular momentum. And if you had a chance to read it, you will see that's what it says right at the beginning. It says, welcome to chapter 11, title, angular momentum. And it talks all about angular momentum. And as I said, of all the analogies between translation and rotation, this one, momentum, is probably the hardest of them. And so the author's given it a whole chapter. Although I'm not sure it, like I said, justifies a whole chapter, because that's why the chapter's kind of short now. It's just one more topic here. And so I'll start with the symbol that we're going to use for angular momentum. It is L. And maybe I should be a little more clear here. If you remember, it was a vector. And so linear momentum is what we'll call it now, as a vector. It's mass times the velocity vector. And angular momentum is going to be a vector also. But we will have a couple of statements to be made about calculating angular momentum. And I'll start off with what hopefully is the obvious one as we've been going through our analogies. Any guess what you might think is the equation for angular momentum? Perfect. In place of regular inertia, mass, we put I, our rotational inertia. And in place of velocity, V, we put the omega. So in place of the linear velocity, we put the angular velocity. So there's our equation. And that's right. However, it's not the only equation, which again is why I said it's a little more complicated, a little bit more involved. But I'll start there. Actually, I'll pause there and start the chapter in section 1, which your author does. And he says, let's do a little bit of mathematics. Let's do what I'll call a math review. Well, the truth is, it may not actually be a review. For some of you it is, and for others of you it has not. As we're getting towards the end of the semester, you might remember that when we first learned about vectors in Chapter 3, I said we're only going to learn to add and subtract vectors in Chapter 3, because later on we will learn how to multiply them. And we will learn two ways of multiplying vectors together. And we already did one, right? We already did a dot product, what we call the scalar product, back in Chapter 7 when we did the idea of work. And now we get to the second way of multiplying it together, which is what we call the vector product, or maybe more commonly known to you as the cross product. And so just like we called the dot product the scalar product, which, like I said, I learned it as the dot product. I can't help but say dot product, but I really like the word scalar product because it tells you what you get. It tells you when you take those two vectors and multiply them together, you got a scalar. And that's what we did for work. So hopefully it doesn't surprise you here. This is saying take two vectors, multiply them together, and get a vector. So the vector product gives you a vector. So again, I like the word vector product, and I'm glad your author uses it, although again, I have a tendency to always keep calling it a cross product because, again, that's the way I learned it, and I suspect that's probably how most of you were exposed to it in your math class. But here's what it is laid out to be here. If you take two vectors, let's just take a vector and call it vector A, and then let's take another vector and call it vector B. You want to multiply those two together. The way you write it down on the board is vector A with a little cross to get vector B. That's why it's called a cross product, right? You represent it with a cross. Now, maybe just for comparison, I should put over here, because like I said, one thing good about these two chapters is that it makes us go through and review a lot of the physics that we've done up to this point here as we compare rotational motion to translational motion, and it gives us a chance to review and either relearn or maybe learn for the first time something we skipped over as we were going through the semester kind of quickly. But in a dot product, we of course wrote it as A dot B. So hence the name dot product here and cross product here. Now when we did chapter 11, we called this vector, we called that C and no vector on it because it was a scalar product. Let me do the same thing. Let me call this vector C. So I'll call it C, but this time I'll put a vector over it because again it is a vector product. Now if you remember how this worked out, we said that you can really do a dot product two different ways. The first way is to say take the magnitude of A, the magnitude of B, and cosine of the angle between them. So if this is some angle between them, we get cosine of the angle between them. And if we examine that carefully, we'll see that B cosine theta is really a breakdown of saying how much of B is projected onto A. And so we use this for work because that was our definition of work, right? Our definition of work is how much of the force, what component of the force is in the direction of the movement. So we weren't interested in the whole force, we were interested in how much of the force is in the direction of the movement. That's where the cosine of the angle came into place. That's why the dot product was a nice mathematical technique to get to our physical picture of how much work is done. And then of course we saw the advantage of work, how the work was the change in kinetic energy, that work energy theorem, which then led to our conservation of energy. So that played a very useful role. So there's kind of our review here. What's going to happen here is kind of the same thing, except what we're going to get is A times B times the sine of the angle between them. And so if I put a little theta here, and I take B and I break it apart now, then this part right here is the B sine theta, this perpendicular part. And so it's really a statement of how much of B is perpendicular to A. And at this point, I would say I have only calculated the magnitude of the vector. And since it's a vector, it has two parts. It has direction as well as magnitude. But again, I'll just start here with my so-called math review or my math class here and say, look, this is what a cross product is. And I'll tell you, it becomes very, very useful when we start dealing now with angular momentum. That's why it's section 1 here of chapter 11. It says, here, let's learn a little bit of math before we deal with angular momentum. Okay, very useful. It's also, I should say, very useful for dealing with torque. We even though we've done torque, we've only done torque at 90-degree angles so far. So we're going to change that as we get into chapter 11 and chapter 12. And cross products become really nice. So there's 2 reasons we'd like to see a cross product. And maybe I should say there's 2 reasons this semester cross product. There's a lot of reasons next semester. So we're going to use cross products a lot. And this is your first formal introduction, or the first useful time that it's been in this class. Okay? So I'll say it again then. What you're really getting at is this part right here is really saying how much of B is perpendicular. So you can kind of see how they are similar but also different. This one is saying how much of B is in the same direction as A. This one is saying how much of B is perpendicular to A. I'll even pause right there and come over here to our last chapter. In our last chapter, we were talking about rotating objects, and we talked about applying a torque to an object. And so if we take a wrench here and we hook it onto a bolt and we grab the wrench maybe right about there, obviously the bolt is designed to turn or to rotate at that spot. And so this is what I'm going to call R, the R vector. How far from the rotational point to where did you apply that force? And then if I do apply a force, let's say I'm trying to loosen it, I might grab the wrench and pull it at some angle like this, F. Notice the force is not perpendicular to R. And when you then analyze this a little bit better, you will see that this part you might call F perpendicular, and this part you might call F parallel. This parallel part doesn't turn the bolt at all. It's useless. And so we don't care much about that. We care only about how much of the force is perpendicular, which is why this becomes quite useful. And so expanding on our idea that we had in the last chapter, where we wrote down torque is R. Did we write R first? And I can't remember which one we wrote first, but R's. And then I wrote sine theta, but I'm going to write it in this order. Well, it doesn't matter. So it looks like this one. But I do want you to see, do you see how what we've been writing in the last chapter is really a cross product? No. Did we call it cross product? No. No. In fact, we didn't have any angles other than 90 degrees, if I recall. But like I said, that's going to change here. So what's kind of nice is we will now start to write torque as this form, R cross F. And that will be a more sophisticated way of writing it, if you will. Saying how much of the force is important. And then how much of that force is important? The amount that is perpendicular. Just like back here when we did work. How much of the force was important? The part that was projected or parallel to the distance it moved here. Okay? And so remember this then, as I write this on the board here, here is our new way of calculating a torque. Two vectors multiplied together with a cross, which means the angles between them. So you've got distance, you've got force, and you've got angle. But the angle's kind of buried in the symbol with the cross product. And don't forget that. Yeah?
What happened to the sine?
I don't need the sine theta. This means, what does this mean? What does this mean? It means take the magnitude of R, take the magnitude of F, and multiply it by the sine of the angle between them. Okay? So again, you don't see it in the formula, but it's there, and that's easy to forget. That's my point. Okay? There is the sign of the angle. We haven't changed that. So again, more so I think the author has done a good job by giving you a whole chapter to see all three factors, R, F, and the angle between them. And then burying that angle in a better notation. You'll see it's a better notation. And you bury it and you don't see it, so it's easy to forget about it, but there's some nice advantages here of writing torque like that. Okay? So again, there are two reasons we would like to talk about a cross product. One of them is torque and the other is angular momentum. So the easiest one to give you is torque because we've already done torque. But there's our equation for torque. Now of course it also is a vector, and I haven't talked about the vector part of it quite yet here. So far all I've done is given its magnitude. So now let's talk about its direction. What direction is the vector C? Well, see if this helps. The direction is perpendicular to the plane that A and B make up. Wow, this is going to require a three-dimensional picture. What is perpendicular to the plane of A and B? Yeah, the z-axis, you might say in a math class, in and out of the board. Okay? And so a simple technique would be to say, take your right hand. So this is our second right hand rule. Remember we did one already before, chapter 11? We said if you wanted to know the direction of your angular velocity, just take your right hand and curl your fingers in the direction that it's spinning. So if I had a disk that's spinning like this one, I could take my right hand and curl my fingers in the direction of the mass. And which way is the angular velocity? Okay, upward, right? Which we usually call positive y direction. Okay, so upward. And so that would be the direction of the angular velocity. Sure, so we learned that right hand rule. Don't forget it, because I'm about to give you a second one, and I don't want you to confuse it, even though we call them, both of them, the right hand rule. There are many right hand rules, and so this is a different one. This is the right hand rule for finding the direction of a cross product. It's a lot to say, so we don't usually say it that much. But we got the right hand rule for finding the direction of the angular velocity vector. And now we're going to have the right hand rule for finding the direction of a cross product. And it's simply this. Go ahead and put your fingers in the direction of the first one. And then close your fingers towards the second one. Okay? That's kind of how you remember it. So you don't want to hold your hand like this. You can't really close your hand towards the second one. Fair enough? And you don't want to hold it like this because, again, you're not really closing your hand towards the second one. You want to hold your right hand in the direction of the first one and close it towards the second one. Some people prefer just to make their fingers do that. And they go, okay, instead of just closing my whole hand, I'll just put my finger in the place of the first one and my other three fingers or my second finger in the direction of the second one. Okay, if you prefer that, that works. But the bottom line is, look at your thumb. Which way is your thumb pointing? That's the direction of C. Okay? So, fingers in the direction of A, closed towards B. Which direction is my thumb? Out of the board. That's what this little prop is for, if this helps. You got to have a three-dimensional picture here. If this is A and this is B, then there's my direction. I've got A pointing off this way. I've got B pointing off that way. Which way, C? Out of the board, towards you. What somebody said, a Z direction. A positive Z direction is usually what we call that. So to label that, we call it vector C. We put an arrowhead. And what we do is we like to put a circle with a little dot. It might be what you would visualize if you ever, and hopefully you've never seen this, but if you've ever seen an arrow shot right at you, that's what you would probably see. You would see this round with a pointy dot at the end coming right towards you. And so there is your directional vector. Now, if that made sense to you, what if I went and called it B cross A? I'll call that vector D for a moment. What do I get there? Yeah, so in this case, lay out the first vector, well in this case maybe I should lay it out, well, this way. I'll do my hand first here. But put your fingers in the direction of the first one, B, and close towards A. Okay, so notice this won't work this time. I can't go B first and then close towards A. My hand doesn't go that far. Okay? So I can't close it that way. And so I would have to close it this way. And I certainly wouldn't do something like this or something like that. That's not closing towards A. Okay? So in the direction of B, close towards A. Which way's my thumb? Into the board here. And so it would look something like this. If this was B and this was A, then B cross A is into the board. And so if you, simply put, if you draw the two vectors on the whiteboard or on a chalkboard or on a piece of paper, if it's going to be perpendicular to those two, it has to be in and out of the paper. The question is it out of the paper or into the paper? And so in this case, D would be into the paper or into the whiteboard, and we like to represent something going into the board, a circle with an X, what might look like if you had an arrow. I don't have a real arrow, but an arrow going away from you, you would probably see the feathers that are glued on the end, and you would see kind of a little circle with an X there to indicate away from you. Yeah?
I don't know if this would ever apply to all cases, but what if theta's 180? How would you tell it's a direction? There's no close.
So what's the sign of 180? Zero.
Yeah, I was just wondering for direction.
Well, the magnitude's 0, so how do you give a direction of something that has 0 length? Yeah, so, yeah. So there's no discussion about its direction when it has 0 length. Yeah, yeah. So fair enough. But if it's less than 180, then yes, then you want to go to the smaller, close it towards the smaller one. Don't try to close it greater than 180 degrees.
Is it for some reason inconvenient to just draw the three-dimensional axes, like bigger than about 200?
No. You mean, you want me to draw?
I wasn't asking you to do it, but is it like not something that's done for the, yeah, like that?
Okay, so I draw the x-axis and the y-axis and the z-axis. And so I have a vector maybe going in the xy plane here, call it A, and I have another vector going in over this way, say B, so the direction is C. Okay, if that helps. And so this is a three-dimensional drawing. So I don't know which is better. I think what you were saying is, I want you to see that C, C, S-E-E, and the vector C, the letter C, right, is out of the board, right? So if you want this, that's fine. If you want this, that's fine too. Whatever helps you the most. But I got to admit, sometimes a three-dimensional picture on a two-dimensional board doesn't get interpreted right by the viewers, right? And so I really like this because there's no doubt which way C is pointing. Okay? Where somebody might walk on up to this and they see C pointing down like that, like it's in the XY plane pointing at an angle, and get the wrong mental picture of the three-dimensional picture. But if you draw your axes, maybe that makes it very clear. Okay? So there's A cross B. And of course, that was the easy one to draw because A and B were in the XY plane. What if the two vectors A and B are not on an XY plane? Maybe the XY plane is here, right? And the XZ plane is the floor. And I've got a vector that way and a second vector that way. So a cross product of A cross B is down that way. So it's not so easy to always draw or to visualize what it is. But it is fairly easy to calculate it, and it'll always that will be the case. But again, as my first math step is then this direction, I guess the answer is the right hand rule. And maybe I should say for cross products. Not to be confused with our other one, and certainly not to be confused with the next 5 we're going to learn next semester as we get into more right-hand rules about electric fields and magnetic fields and all those good ones. So by the time you're done with these 3 semesters, you'll have a lot of different right-hand rules. I will say this 3rd test, we'll see next Wednesday, but I can just watch students in the stress of the moment, and not so much this class, really maybe more the next class, but they start doing all their right-hand rules busily while they're trying to calculate. And what's wrong with that? It's your left hand. Okay, you don't use the left hand for the right-hand rule. Okay, as funny as it sounds, it needs to be said. So in the stress of a test, put down your pencil. Unless you're left-handed, put down your pencil and do the right-hand rule with your right hand. Sure.
Like that. If it's up, it's really down.
Okay. If that helps, then you don't have to put down your pencil here. Yeah. So certainly it could have been done with the left hand, but probably because the majority of people are right-handed, they call it right-handed. But I guess the right-handed person wasn't very smart. Most right-handed people aren't. I understand. and no, I just kidding. So.
One of those is magnitude, right?
Okay, good point. Good point. If you'll notice that, and I'm building up to that, is that the cross product is a little bit harder than the dot product. The dot product just gave us a number, gave us a scalar, end of story. Here, we've got to do 2 things. Number 1, we have to calculate its magnitude, and then number 2, we have to calculate its direction. And that's why I have this formula which only gave it its magnitude, and that's why I did my right hand in order to find its direction. And what you've noticed over here is I have inadvertently put this step, which is a vector, and I set it equal to a scalar. And so what I really mean in this step is this is just how you calculate the magnitude of the torque. So if I come back over to this picture here and I say, all right, now let me take my right hand, and I put my fingers in the direction of the first vector, there's R, so R would be pointing that way. Close it towards F, so there's R pointing down, and I'm closing it towards F. It gets which way? Out of the board. And so this really should be RF sine phi in the k-hat direction. And now it's a vector. Not only do I have its numerical value, its scalar part of it, but I also have its direction. And notice it's positive, and so positive would mean that it is giving a torque, forcing it to rotate in a positive direction. And sure enough, this bolt, as I pull it, would rotate in a positive direction. And so this bolt rotates in a positive K, which was our first right-hand rule about something rotating. Take your right hand, curl your fingers in the direction of the mass, and it's pointing out of the board. So this object is rotating in a positive direction, which of course, because I gave it a torque in the positive direction. Yeah?
Wouldn't it be F cross R if it was going to be positive?
No? So let me put a grid here. Which way is R? So here's R. Which way is F? There's F.
Oh, okay. I thought R was going out.
Oh no. Okay. Good. Yeah. Good point. Got to make sure we're clear. R is coming out from the axis here. R is not going from what your holding point in. Yeah. Yeah. So yeah, we got to get the same. Right. Yeah. But I guess you could define it the other way and then do the left-hand rule. Then you don't put your pencil down. No, but too many options can get confusing. So this is what the author does, and this is kind of tradition, and I like it, so I'm gonna stick to it, even though the whole book is very chauvinistic and favoring right-handed people the whole time. I know, but does it all the way through. So at least it's consistent. I'm joking, of course. You know, there is a society of left-handed people. Do you know that?
There's scholarships for left-handed people.
Oh yeah, and then sometimes there's scholarships specifically for left-handed people. That's right. Yeah, that's right. So, yeah. So, but yes, I do I do recall getting literature from the Left-Handed Society people many times. So, and you could buy things like left-handed scissors, left-handed guitars, left-handed golf clubs. Guess there's no such thing as a left-handed bat. They're pretty symmetric. So, all right. So, all these things that are so discriminatory for us left-handed people, right? Anyways, obviously I'm playing around here, but I'm hopefully this makes sense, the direction. And I'm not done here with the math yet. Let's go one step further, because we saw the same thing back when we did here. So let's jump all the way back to chapter 7. Didn't we have 2 ways to do the dot product? We did, didn't we? Do you remember the second one? Yeah. If we knew the components, we just take the x components and multiply them together, and then take the y components, multiply them together, and then add them together, and so that comes out to be the same magnitude. So we should have the same kind of thing here. We should have a way of doing a cross product also that would be useful, where it can involve the components. And yes, we can do that. It's a bit more complicated, especially since it's very three-dimensional oriented. I could do the dot product in 3 dimensions, although doing the dot product in 3 dimensions doesn't make it much harder. We just have A in the z direction and then B in the z direction, and so that's hopefully pretty obvious. But the cross product in 3 dimensions requires you to know how to do a matrix and a determinant of a matrix, which you may or may not be familiar with. So let me show you. Here's what it says to do. If you, and I'll transfer it over to here, so the vector C equals, and you write out a determinant, a 3 by 3 determinant. And what you do is you write the unit vectors first, then you write the first vector as it is listed, and then you write out the second vector as it is listed. And I don't know if this helped you. This was your question about the drawing there, but instead of drawing it, I can just do this determinant, and I can get each of the individual components. And so how do you do a determinant? Yeah, you expand it around 1 row or 1 column. And in this case, it would make sense to expand it around the top row, since those would be your components. So I would expand it around this first one, which is the I hat, which would then lead to the second one, which is the J hat, which would then lead to the third one, which is the K hat. And maybe I'll change colors, but if you remember determinant, or if you don't, let me show you. You think of it this way. You go to the first one and you cross out its row and column, and then you're left with just this 2 by 2. And you kind of go in a diagonal and you multiply them together, A, Y, B, Z, and then you kind of swoosh around and subtract the A, Z, B, Y. And so that would be the expansion of that matrix. It's the first one. Then you go to the next one and you essentially do the same thing, except don't forget to alternate signs. So minus, plus, and we're at the end. And so now, maybe changing colors would be helpful. I'm looking at the J component, so I can cross out that row and that column. And again, I can do a little swoosh. So it's AX, BZ, AZ, BX. So AX, BZ minus AZ, BX. And some of you are looking at me like I'm crazy. Do you not do this? Do you do it different? The swoosh? You shouldn't call it the swoosh, huh? Okay. Okay. So there would be the second one. And so now if we finish the expansion of our determinant, and one more color, how about a black? Do I have a black up here? Same idea. Again, cross out the row and the column according to the third one, which is the K. So I'll cross out that row and column and then kind of do a swoosh. Now it's really getting messy up there, but it's AX BY minus AY BX. Whew. If it's any consolation, it might be easier to remember. Since it's a cross product, they should be perpendicular. So did you notice the X component has no X's? The Y component has no Y's. And the Z component has no Z's. And so maybe that would help you. I must admit, especially for this chapter and into the next chapter, this is probably going to be the easiest way to do the cross product. You can get the magnitude by doing this. You can get the direction by using your right hand. Something a little more sophisticated, something a little more three-dimensional and a little more complicated, we'll wait till later. So many of you in the fall will be signing up for our statics class, and you'll be looking at a bridge, and you'll be looking at the forces and the torques in a three-dimensional picture, and you've got to figure out, okay, here's the bridge. What is the chance of this bridge rotating X, Y, Z? And you need to look at then the torques on all three axes. Most of what we do, especially here at the beginning, is to say, look, our two vectors, if our two vectors are in the XY plane, okay, and so as we've been drawing them, A and B, if they're in the plane XY, that means the Z component is 0, right? And so let me look at that. If AZ is 0 and BZ is 0, what happens here? 0, 0. Goes away, right? So what you're saying here is there would be no rotation, no torque around the x-axis. Makes sense. If you apply a force anywhere in this plane, it tends to make it rotate around a z-axis. Nothing is going to make it rotate around an x-axis. So that one goes away. 0 I hat. Same thing can be said here about the j hat. A 0 here and a 0 here, that one goes away. The only thing that doesn't go away is the fact that you are going to have a rotation, and so our rotation will involve the x and y components of the vector A and B, and that will only give you a rotation around the z-axis. So I thought I should give you the whole determinant for a good starters, what will help you in the future, but for this chapter, most of our things will be straightforward, that they'll only rotate around the z-axis. Next week's lab is a good example of that. You are asked to take a platform like this, and you are asked to pull on it here, and pull on it here, and pull on it here, and pull, but you're always going to pull on it on a plane like this. Which when you pull on a plane, what does that tend to do? Make it rotate around this axis only. And so we'll call that the z-axis, and so all of our tugging in the xy plane only allows it to rotate around a z-axis. But it's a good lab to do, even though it doesn't allow it to rotate this way. But of course you can see in the real world it might do this and this, right, at the same time. And so if we have a satellite, which is why we have to discuss it, maybe not this semester, but soon in our education on mechanics, about the possibility of rotating around all kinds of axes. So again, that's why your author sections out this first section and says, let's take a moment to do some mathematics. All right, so now that we've done some mathematics, you hopefully now see this idea of a cross product, and you see that now we are going to write torques not in the form with the angle in it, the sign of the angle, but in this form with an R cross and an F. And so from here forward, that's how we'll write our torques. So now let's really get to angular momentum. We haven't really done any angular momentum other than the very beginning step where I said, what do you think the equation is for the angular momentum? Can you take a guess? And you did guess, and guess correctly, that the angular momentum would be the rotational inertia times the angular speed. Now, the reason I stopped there is because I was trying to show you this cross product, but let's take a close look at this then. Okay? Let's look closely at it. And let's say, all right, angular momentum is I omega. True. Let's simplify our discussion here a little bit and say, let's only allow it to rotate around the z-axis. So let me draw a picture here. Let me take some odd-shaped object, put a nail in it, and spin it. Okay? And as it's spinning, I claim that that thing spins in a circle. It has some angular momentum. That's what this chapter is about. And how do you calculate it here? Well, you can hopefully see why this definition is so useful. Let me break this apart a little bit. First of all, let me just call it L without a vector so that, I'm just talking about a rotation around a z-axis. I'm not worried about direction. But let me change the I to the sum of mi/ri squared and then this omega. Okay? Now, I hope you remember that. This is what chapter 10 was and what I think you're working on, and like I said, why I wanted to do so many examples for you last time, because I think calculating moments of inertia, understanding moment of inertia, is one of the hardest things we do this semester here. But if you look closely at this, what is this saying here? Well, let's take a little chunk out here. Let's look at that chunk right there. If you look closely at that chunk, call it the ith chunk, has some radius r some I. That's what is meant in this formula, right? It means that this chunk has a mass of m sub I, so there's the chunk. It is at some distance r sub I. If you square it and multiply it by its angular speed, that would be the angular momentum of that ith piece. In other words, the angular momentum of the ith piece is the mass of that piece times the radius squared of that piece times its angular speed. Fair enough? Now, let me do a couple steps here. I'll start with leaving the m and one of the r's alone, but what happens when you take the omega and group it with one of the r's? What would you call that? Yeah, that would be the translational velocity, wouldn't it? And now, what would you call this m together with the translational velocity? It's linear momentum, right? It's called linear now, so we don't confuse it with angular. But so this would be your r, and then this would be your linear momentum. And so when you view it in this way, you'll begin to see that what you're really saying here is the angular momentum is like the linear momentum. In fact, it is the linear momentum and distance. And isn't that what we said torque was? Wasn't torque really force and distance? And so we're really saying the same thing. And that's what I wanted you to see. This is really saying the angular momentum of some ith piece is the linear momentum times its distance away. And of course, this has overly simplified it a little bit, because this piece, as it spins around in a circle, and it is a rigid object, can only move in a circular pattern, right? But what if it was something that looked like this? What if it wasn't a rigid object? What if this was the axis point, maybe call it the sun, and then this is the object, maybe some kind of asteroid or comet, and it was headed off in that direction, v. How do you think you might calculate the angular momentum of that one? Yeah, and good. I'm glad you're seeing the idea that you would say, well, I'm only interested in how much of the velocity is then perpendicular to it. The fact that it might have a velocity heading radially outward from the sun or radially inward isn't what's relevant. What's relevant, as we see here, is how much of the velocity is transverse. So maybe it would make more sense to write it this way, that the radial piece times the momentum piece times the sine of the angle between the r. So in other words, if this is the r going out and this is the real velocity going at an angle, then what I am interested in, of course, is the sine of the angle between them. This being the angle between them, then how much of that velocity is perpendicular? Now I think you can see why we bothered to spend the last 20 to 30 minutes talking about cross product. Does this look familiar? Doesn't this look anything like what we just did with torque? Couldn't you write this then as the angular momentum is equal to r cross p, two vectors multiplied together, where we won't forget that there's the sine of the angle between them? And that's why when I started this a half hour ago, I left this alone and said r cross p. That is another way of looking at the angular momentum. And so if you look at the angular momentum of one piece, it's r cross p. Then if you add them all together, you get the total sum of all the pieces, and then you get this. Okay? And that's just this process backwards. If this is the angular momentum of the ith piece, ith piece, ith piece, ith piece, ith piece, then you add them all together, and you get the total. And the total is the sum of all of these. So this is your I, this is your omega, and this is your L. So whichever way is easier, and I should point out, whichever way is easier depends on the problem you are doing. Usually if you're looking at a single point object, it tends to make a lot of sense to do r cross p. If you're looking at an object that is rotating, since each individual piece is rotating at a different position when with a different speed, then it would probably make more sense to do your angular momentum that way. And so we've got our two options for our angular momentum. This, like I said, is for, you might call an individual particle. But if you add up all your individual particles together, then you get the total angular momentum of your spinning object, which in this case would be a disk. Do you have a question?
Is R the position from the center of mass or the radius?
From the rotational, so the axis is probably the way to answer it. Because we don't have to be rotating around its center of mass. Yeah. As you saw in the last chapter, we did that a couple times with a meter stick, where we said rotate around that, that point there. Yeah. And so even though its center of mass is here, we don't have to rotate around that. Yeah. So we're back to what we are currently learning in chapter 10. But in order to do these problems in chapter 11, you'll see that to get the angular momentum, you'll need to know the moment of inertia. Moment of inertia and angular speed are very important as they lead into this chapter to find what's the angular momentum of our object. Okay? And so there's the whole idea then. Okay? Now, maybe as a quick example, just because I think the angular momentum is a little bit harder than any of the other rotational stuff, is what if I just came over here and then I said, all right, help me out here. Could you calculate the angular momentum of this ball spinning around in a circle? What would you do? Yeah, well, it's kind of like a single object, so I do the cross product, right? Maybe I draw a picture first. I say, okay, so here's the center, here's the circle, here's the ball, some radius r out there. It's got some mass, it's moving with some velocity. Okay, to get the angular momentum of that ball, I would go r cross p. And in this case, the r And I'll just do magnitude first. There's R, there's P, and there's the sine of. Yeah, and I picked the circle first because it's 90 degrees. And so, well, that one's going to be easy to do, right? 90 degrees. And then I just get my R and my M and my V. So RMV is the angular momentum of something going in a circle. So a single object going in a circle, pretty straightforward. Some of you might even remember that from 102. That's the only formula we gave you in 102 for angular momentum. It's the simplest one. Single object, going in a circle, that's it. But what if it's not a circle? What if it's more elliptical in nature? What if, say, this is the orbit of some planet here, and it's got a more of an elliptical shape to it, and the planet is right here heading off in that direction. So when you draw the R and the V vector, it has a mass m, and there is some angle between them, maybe call it phi.
Is that the center, or is it just the right?
Well, this will be the sun or the star, you know, if it's some exoplanet, you know. So they find this exoplanet, it's very elliptical, and they want to know what is the angular momentum around the star that it is orbiting. Okay, well, how would you do that one? This one's a little harder, but not too much. Answer. But still a point. So I would still do this. And then I would have an R, a P, and then what? Sine of phi, right? So here I would have an angle between them. Now if I write it out, then I would have this R and V sine of phi. So we didn't have that over here because it fell away with the 90 degrees. But hopefully you'll see it's really the same logic that I would get the angular momentum, right? And I would just have those three factors. What is R, what is M, what is V, and what is the angle between them? Yeah.
Wouldn't R be changing there?
Oh, now this would be at that instant. So now you've asked a deeper question, right? What about a moment later? And maybe I'll change colors here. But, and maybe more than a moment. Maybe a month later you look at the planet and it's here. Isn't that a different R? Uh-huh. And then maybe it's a different angle too. A very good chance it's a different R. Very good chance it's a different angle. Also a very good chance it's a different speed. Now it's a little too early to probably prove this or tell this to you, but we're going to see that the total angular momentum didn't change. Hence, conservation of angular momentum. See, didn't we have a conservation of linear momentum? And wasn't that very convenient as things interacted? Well, here we're going to have conservation of angular momentum, and it's going to be very nice here. So this one, it may not be so obvious yet, but in this one, the R, in the picture I've shown, this gets smaller, but this gets bigger. And this changes too, and it looks like this gets a little bigger. So between this getting bigger and that getting bigger and that getting smaller, when you multiply them together, you actually end up with the same thing. And like I said, a little early for me to say that, but maybe within a half hour I'll say that and say, look at this. This is our proof that the angular momentum doesn't change. But you're right, we would have to calculate it at that moment. What is R, what is V, what is phi at that moment?
Well, I'm just curious. In space, would there be a lot of, there's not any
No.
air over there, so,
Yeah, no air resistance. So, yeah.
but there is gravity to make it over there.
So there is gravity that makes it go in the ellipse. Yeah. All right. Well, those are, I think, the two easiest calculations. And I'm hoping this one won't be too bad. What if, and here's what you're going to be doing a lot in the lab here today, what if you just take something like this, a disk, and spin it? What would be the angular momentum of this one? Yeah, now this is my point. So in this case, I'm not looking at a single point, although I could treat it as a single point and add it up. But isn't that what this is? And that's what I'm trying to show you. So I would jump away from this one and jump over to that equation, the other way of doing it, because the I is the summation of all those points. So doing this calculation, I would say I omega, then, it's a terrible omega. Okay. But the angular momentum is equal to I omega. And then I would pause and say, well, how do I calculate the I then of a disk? Answer? Yeah, and so we work this one out. It comes out to be 1/2 mr squared, where m is the mass of the disk and r is the radius of the disk. And then times the angular speed squared. Okay? And so that's how I would calculate. Now all of these have direction. So far I've ignored all that. But it is a vector, it is a cross product, so let's talk about its direction. I'll start with the circle again. What direction then is the angular momentum vector? Yeah, fortunately we got two options. The two options are both of the right-hand rules. We could do the right-hand rule for rotation of a mass. That's probably the easiest one. Just take your fingers there and curl your fingers in the direction the mass is moving, and you're going to get out of the board. Now that one's probably so easy, we should probably do the other one. The other one is the cross product one. The cross product one is put your fingers in the direction of the first vector, there's R, and close them towards the second vector, which is the P, which is in the direction of the V. So R cross P is out of the board. So either way you want to do it, you are going to get an angular momentum vector, right? It's got a magnitude and it's got a direction. And so yeah, it does come out of the board. Same thing here. We can take the direction the mass is spinning, okay, which is this way, and our finger, and again we get out of the board. Or we can do the cross product. That is, we could put our fingers towards the direction of the first vector, close it towards the momentum, and get out of the board. So either way, both of these are a rotation in a positive direction. That's why we call it counterclockwise a positive direction. And this thing too not only has a magnitude, but it has a direction. So if I come over to here, and I say, well, what direction is the angular velocity? Because I did it this way, and the direction of the angular momentum would be the direction of the angular velocity. I could take my right hand, curl it in the direction that the mass is spinning, and in this case it would be up, which we usually call the y direction. So I will continue to call that the y direction, and I would say then it has an angular momentum vector in the j direction. Now let me give you another calculation here. What if I have not just this disk, but I have this ring placed on top of it? And the two are rotating. How do I get the angular momentum of that one? Answer? Yeah, don't I just add the two inertias together to get the total inertia now of the system? And the total inertia of the system here is, of course, the two together. So I would have then the I for the disk plus the I for the ring, and then I would have the angular velocity. Now, hopefully I'm not surprising you too much, but I wanted you to see these calculations. Guess what you're going to do in the lab? Yeah, you're going to do a lot of this. You're going to do a lot of calculation for angular momentum. And you will need to do, like I said, in one case, this one. What is the angular momentum of that one? And then you'll be doing this also. What is the angular momentum of that one? But the real point of the lab is something even more than that. Do you remember that principle, conservation of linear momentum? Now, we didn't say linear momentum when we were in chapter 9, but what did conservation of linear momentum tell us? What was neat about that principle? Well, as the name implies, the momentum before is equal to the momentum after. Now, wasn't that only true if you didn't have an outside influence, right? Okay, so do you think, by analogy anyways, we're going to have kind of this same thing? We will call it then conservation of angular momentum. Any guesses on that one? What it might say? The angular momentum before you do something equals the angular momentum after, as long as you don't have an external torque. Good. Not forces, torques here, right? You don't have torque. Right. And so it's exactly the same. In fact, we kind of reach a real milestone here now. We have learned what I've been saying from the beginning now of this semester, that here's what we're after. Newton's 3 laws of motion and the 3 conservational principles. We've learned Newton's 3 laws a long time ago. We've learned conservation of energy a long time ago. We just kind of recently did linear momentum, and now we're in the middle of a discussion about angular momentum. And no new physics from here until the test. After the test, we'll get more physics after the test. But between here and the test, 9 days, no new physics. You got 9 days to learn it. All I'm going to do for the rest of this chapter is examples of this. And into chapter 12, apply the stuff we've learned to building bridges and buildings and roads. But no new physics. So that's the good news. And I like the way this section drops down that way, because I know that you're going to need 9 days to digest all of this. Even then, you might feel a little overwhelmed 9 days from now when you come into the test. But I hope not. I hope that, that gives you a lot of time and me to tell you, no new physics. Start learning it now. You don't want to wait till the night before. You can't get it all crammed into the brain and let it settle. You got to learn a little bit, let it settle. Learn a little bit, let it settle. Learn a little bit, let it settle. This takes a while to sink in here. So this idea of conservation of angular momentum is very important. In fact, you of course saw that in 102. Here's a good example of conservation of angular momentum. Here is a spinning object. It has angular momentum. Here's a non-spinning object. It does not have angular momentum. What do you think might happen if I put the two together? That one's probably going to slow down. Right? It's going to lose angular momentum. And where does it go? To that one. And so the angular momentum before I drop it is equal to the angular momentum after I drop it. And so you can go through a little bit of math and show that. In fact, you are going to do that in the lab. You're going to do this. What's the angular momentum of that one? And then you're going to hold this one in your hand. That one should be easy. What's the angular momentum of this one? 0. What happens if I put them together? This one will slow down and lose angular momentum. This one, speed up and gain. And now if you figure out the angular momentum after you drop them, guess what? It will be the same before and after. And that's the whole point. So you got your little computer, and you're going to measure this speed, you're going to get its mass, its radius, you're going to get the angular momentum of that one, and then add 0 to it. Then once you drop them together, the little computer is going to give you the new speed. And the new speed is going to give you the new angular momentum. And you're going to say, hey, what is the angular momentum? And so you're going to say, what's the angular momentum now? You're going to compare it to what you did before you drop it, and hopefully the two are in agreement. Conservation of angular momentum. In fact, let's keep going with this. You probably saw this one. I did this in 102, where you said, well, what if you don't drop another object on it, you just keep the same object, but you start with the weights out here. What happens when I pull the weights in? I better put my leg over there in case I go over. So why do I change my angular speed? Yeah, so good. You see it. It's the principle of conservation of angular momentum. I'll say it again. The angular momentum is conserved as long as there's not some kind of outside torque on it. And so there's no outside torque on me, or at least very little. This does have a little bit of friction, but it spins pretty good. And so it freely rotates. And so what you're saying here is my angular momentum is not going to change. But what did change is I pulled the weights in. And what you just learned in chapter 10 was part of rotational inertia is the positioning of those. So when you bring them in, they have less rotational inertia. So in order to have the same angular momentum, if this gets smaller, then this has to get bigger. Or then when I move my arms out, that gets bigger, so this has to get smaller. And so we have, again, a conservation of angular momentum. And in fact, it's going to be the second experiment you do. After you do this one that I just showed you, you are going to take it apart, and you are going to do something like this. And this object can go out or in. And so to test this one, you will do something along these lines. And you will have the weight out here, and you will spin it. You will measure its angular momentum. And then what? Pull the weight in. Measure its angular momentum. Hopefully, they will be the same. And if you want, you can let it out and let it in. But you don't have to do that for the lab. You can just let it out, let it in. Okay? And you can get the angular momentum. And that's the point of the lab. Now, maybe in passing, I should say, getting the angular momentum is not so hard for this lab. I think, believe it or not, what is probably the hardest part of this lab is actually last week's lab. Because to calculate angular momentum, you need to know what? Well, it's angular speed and it's rotational inertia. Now the computer picks up the speed for us, so that's easy. You just hit collect and the computer picks up speed. But how do you get rotational inertia? Does depend on the object. So how did we get it last week? Do you remember? And don't worry, I'm going to remind you in lab, because I think, well, believe it or not, I got to remind you more about last week's lab than this week's lab. Do you remember that we put a weight at the end and we hung a weight and it rotated around? You remember this magical formula we had? That the rotational inertia was equal to R alpha G minus alpha. Is it alpha R? I'll need to check on that, and we'll derive it in class again. But I'm pretty sure that's what we worked out last week, and we did it in class. So what you have to do is you have to put the weight, say, in this position and lock it, and then hang the little weight and let it spin. And use that information to get the rotational inertia when it's at this point. And that's before you even do the experiment. Then you have to put the little weight in here and lock it, hang the little weight again and let it spin, and go through this equation to get the rotational inertia. So you have the rotational inertia in the two positions. And what you're going to see then is the I1 omega 1. What does it equal compared to what I'll call number 2 when you pull it into place? So you've got to use last week's information about hanging the little weight. Okay? But once you hang it in these two spots, then you can actually do the experiment. You know what it is here, and then you know what it is here. And so you get your two different speeds, and hopefully you get the same angular momentum for each of them. The same thing can be said back here. I didn't say it, thinking it was pretty obvious, but maybe I better because it's not so obvious, is how are you going to get the rotational inertia of this guy? Well, same way we did last week. We're going to hang the little weight. And so before we even do the experiment, we just hang the little weight and let it unwind. And let it go down. And if you remember, that was like a 0.0098 or something like that. Okay? And so hopefully we'll get that same number. So we need to know what that is. And also, before we do the experiment, we need to hang the little weight here and let it go down and find what's the rotational inertia of the two together. Okay? So then you can finally do that first experiment where you spin it, use the computer to get its speed. You've already done the experiment to get its rotational inertia, and so from that you know its initial angular momentum. Then you're going to drop it on, and again the computer will record down that new speed, and you've done the little experiment to find its rotational inertia, and you see if they agree. So as I said, there is 1 and there is 2. There's a third part to this lab, which I think is still harder still. So let me do another calculation. Let me move away from the lab for just a second here and ask you something that I think might be a little surprising. I know when I first saw it, it was surprising to me. Even second and third time I saw it was still a little surprising. And that is this. Let's take an object that is just going in a straight line. Object, mass m, velocity v, okay? No gravity, it's not turning, okay? No forces. Newton's first law says object going in a straight line, what does it do? Continues, goes in a straight line, same speed. Does that object have any angular momentum? Well, see if this helps. In the last chapter, when we took a rod and we said, okay, let's spin this rod. Does this rod have a moment of inertia? Yeah, how much? What is the moment of inertia of a rod?
1/3 and also.
About its center.
The question is about what point, right? You can't answer that question. You can't tell me what the rotational inertia is because you gotta have the rotational inertia about 1 point. So if I said, what's the rotational inertia about the center, you would say 1/12 ml squared. If I said, what's its rotational inertia around its end, you would say 1/3. We did both of those. And we could do something in between or even something further out. But the point is, you cannot ask the question, what is the rotational inertia of an object until you also say, about what point? Isn't the same thing true for torque? And what I want to emphasize, the same thing is true about angular momentum. So when I stood up here and said, what's the angular momentum? Your answer is? Is that what you're going to say? You still have a question? Or did I answer your question?
No.
Okay. All right. So I'll say it again here. If I were to stand up here and ask you this question, what is the angular momentum, or does it have any angular momentum for an object going in a straight line? Your response is, about what point? You cannot answer that question. You cannot answer it because to calculate angular momentum, what do you need to know? You need to know distance away. What are we talking about here? So, let me draw 3 scenarios. Let me take that same object and put it more in the center of the board. Here's M, here's V. Let me put the origin right there. I will call this angular momentum number 1. But what if the origin was down here? Angular momentum number 2. What if the origin was up here? Angular momentum number 3. Okay? And so this is the part that, like I said, I think comes in as a surprise. Hopefully not too much of a surprise when I ask it this way. What is the rotational inertia of a rod? About what point? What is the angular momentum of an object traveling in a straight line? About what point? Right? It has to do with your coordinate system and how you set things up. So you can't do any rotational calculations until you define what your origin is here. And now we can do it once we define our origin here. And this might surprise you. Let me do this first calculation. What would I get here? Well, wouldn't this be RP times the sine of? I guess I'd call it more 180 than 0, but either way, calculation comes out to be the same. Because I would say this is R. So R is pointing that way. Which way is the linear momentum? That way. The angle between them, 180. Sine of 180? 0. So how much angular momentum do you have? 0. And the fact that it goes in a straight line and has 0 angular momentum doesn't usually surprise people. It's the next one that may surprise you here. Let's look at number 2. What's the angular momentum here? Well, it'll be R, P, and sine of some angle. And so if I were to draw a line out there, then this would be R. This would still be P. This would be the angle between them. And does that come out to be 0? It doesn't. In fact, if you make a triangle out of this up here on the board, and you call this distance D, so in other words, D is the distance this origin is from that one, then if you put R together with sine phi, that is D. And this would be dmv. Now you said, would it be a minus d? Why do you say minus d? Okay, so the distance goes down, but with that in mind, remember I'm doing a cross product, and the magnitude is equal to the magnitude times the magnitude times the sine of the angle. Okay, so I know d is a negative number down, but no, I wouldn't put a negative d here. Okay, now don't confuse that with what I'm about to do, because I am still going to put a negative here, but I don't want you to confuse it. That's why I was asking you about why did you say negative. So I am not putting a negative d because it is down. I am going to put a positive d because I am dealing with a cross product which says magnitude, sine of the angle. Okay, now that's just the magnitude, but doesn't it have direction? How do we get the direction of a vector? That's our right-hand rule. So which way is R? So R's up like this. Which way is P? P is this way. Take my right hand then, put my fingers in the direction of the R so that I can close my hand towards the P. So which way is the angular momentum? Into the board, negative k. So when I write it as a vector, angular momentum number 2 is d and m of v in the negative k hat direction. And if you want to put the negative first, then I get a negative, and it kind of looks like a negative d, but that's, like I said, not why I put the negative there. It's not that it's down, it's because it's the cross product. And so there's the angular momentum. By the way, this then is a good example to illustrate what would happen a few moments later. Well, the ball wouldn't be here, but it would be here. And you go to calculate the angular momentum, what would you get here? Wouldn't you still get 0? So if you'll notice something, this origin said you should have 0 angular momentum here, and when it gets closer, you still have 0. What does this one say? What happens when the ball's here? Did R change? Did the angle change? Now, if it's going in a straight line at the same speed, P didn't change, right? But did the total amount of angular momentum change? No. Because no matter where you are along this line, as r gets smaller and as theta gets bigger, they multiply together to always give you the d. And so dmv doesn't change. And so there's my illustration of the angular momentum didn't change. Remember we talked about that elliptical orbit a little while ago, and I said it's a little early to say that or prove that, but there is this principle called conservation of angular momentum if there's no outside torques on it. And so that little planet going around would have conservation of angular momentum. Let me expand on that in just a second here, but do you see it here? That according to this calculation, it has zero angular momentum all the time it's approaching. According to this origin, it has a negative angular momentum the whole time, and it doesn't change its value. Hence, conservation of angular momentum. Okay? So, yes, this is illustrating two things. One, angular momentum for an object going in a circle. Yes, and it depends on where you calculate it from. Okay? The angular momentum is a function of where you calculate it from, just like rotational inertia is a function of where do you calculate it from. What's going on in the problem here. Okay? But it also illustrates this conservation of angular momentum. There's no outside influences, no outside torques. That's why this thing goes in a straight line. That's why if you use this as your origin, it has 0 to begin with and 0 to end with. Or if you use this as your origin, it has negative dmv. And at the end, it still has negative dmv. So it has the same angular momentum. Now if I go to the top one up here, how do I calculate the angular momentum? Yeah, and I hope you're seeing the same thing, that this would be my r, this would be my angle. Let me this time call it phi so that maybe it's not the same angle. But when I go to calculate it, it would be r, it would be an m, it would be a v, it would be a sine of phi. And then if you look closely at a triangle, this r times sine phi would be this distance. Let me call it h, I guess, so you don't confuse it with the d, because I'm not saying they're the same distance. But what I am trying to say is if you put the r and the sine phi together, you get your h, your m, and your v. And notice carefully at it that as the object gets closer and closer and closer and closer, yes, the r changes, yes, the angle changes, the m and the v doesn't, but the product of r times sine phi is always the h, so you always have the same angular momentum, hmv, conservation of angular momentum. And again, that's our third conservational and important principle. Again, that's why you're going to be doing the lab here, conservation of angular momentum. Now, we should do direction also, because remember, it is a vector, and at this point, I've only done the numbers. I've only done the scalar part of it. So if I get my right hand out here and say, all right, here is my, where's my origin is here, and there's my r, and there's my p. So as I put my fingers in the direction of r, and I close them towards p, I get out of the board, and so this would be a k-hat direction. Again, hopefully illustrating the point, don't I get a different amount of angular momentum depending on where I calculate it from? Here I get positive numbers, here I get 0, here I get negative numbers. In fact, anything down here would give me negatives, right? Further down, the more negative. Up here, anything up would give me positives, and further up, more positive. So there is my angular momentum, my conservation of angular momentum, and illustrating that the angular momentum depends on where it's calculated from, which is the whole reason we do the third part of the lab today. And the third part of the lab is going to look something a bit more complicated. I'll take this off. I'll put this back on. I'll take this stuff off here. But the third part is to show you that an object going in a straight line does have angular momentum, And you still have the principle of conservation of angular momentum. Because what you're going to do is you're going to put this little catcher. And if you look closely, this ball, if it gets shocked, you can get kind of wedged up inside. So I will place the catcher on here. Pull it around here so it's good and tight. And in the lab we'll kind of angle this up a little bit better. And we'll also take the time to level it. Is mine level? Oh, not even close. All right, but assuming that it was somewhat level, if I put it here, it would stay here, because then, here's my cannon. So, put the ball in the cannon, load it up. And then, carefully align it. Okay, so make sure we don't hit. Looks pretty good, but you are going to use conservation of angular momentum. And you're going to measure this angular momentum after you fired it. What do you know about this angular momentum? It equals the angular momentum before the collision, right? And the angular momentum before the collision came from an object going in a straight line, which is related to its distance and its velocity. So couldn't you find the speed at which that ball was fired? Yes. So you get to do it again. I think we've done that a few times. Calculate the speed at which that cannon fires the ball. And so we're going to do it again using the principles of conservation of angular momentum this time instead of linear momentum as we did last time. Okay? And so there is the whole idea of the lab here. A few quick examples of conservation of angular momentum. In fact, I was watching it this weekend. Not exactly real life, but maybe I should do a helicopter first. I'll do a helicopter first. I mean, what happens to a helicopter if it was, say, you know, on the ground, no blade spinning, and then the blade starts spinning clockwise? Doesn't it got to go counterclockwise? Unless, of course, there's some outside influence on it. So why do you have the tail rotor? Yeah, to supply that torque to keep it from going that way. And that's sort of what this one is here. If I were, you know, this helicopter here, okay, and so here's this helicopter, and so the engine inside starts spinning. Whoops. All right, well, we'll worry about that one later here. But if I forgot that was on there, I would have made it easier to spin. But if I am, you know, off the ground here, you know, when it spins one way, I spin the other way. And of course, if I stop it, hopefully it fairly stops. If I were to spin the other direction, then I would spin the other direction. And so the idea here is before I started spinning the rotor, my angular momentum was zero. So if one goes clockwise, the other one goes counterclockwise. Now, the reason I was kind of thinking about that is I was watching this muscle car, and the guy's revving the engine. So what's going to happen to the engine? Well, you rev it, it wants to go this way. So what does the car body want to do? Yeah, it wants to go the other way. Now, fortunately, the car body does have an outside influence, which happens to be the road. I guess if this was floating in outer space, and they rev the engine would go this way, and then the body would, yeah, rotate the other way. But you can see the whole body rock as it goes in a back and forth motion here. The boats. Racing boats are a good one of this because in general they're light, and so what happens if you are on the boat on the water and you really give it a lot of gas? So engine goes one way, boat goes the other way. And so if you look at many of your high-powered racing boats, how do they do that? How do they compensate for that? And yeah, somebody said transverse engine, but I wasn't going that road. But what if you had a second motor? Right, one going clockwise and one going counterclockwise. So I was down at the harbor and I was looking at the props and the propeller, and you can clearly see one is designed to go clockwise and the other one is designed to go counterclockwise. And so there's no, of the boat, kind of like a big helicopter, the double rotor helicopters, right? They don't need the tail rotor because one prop main rotor goes one way and the other main rotor goes the other way. And so they're familiar, and the designers here are very familiar with this whole idea of conservation of angular momentum, and they obviously have taken that into consideration as they go to design it. The same example I gave you guys in 102 is a good one. What about this cat that you hold by its feet back to the ground and you let it go? Don't try it at home. But most cats do what? Okay, they land on their feet. How do they turn their bodies over? Yeah, if they have a tail, not all cats have a tail, but if they have a tail, they can spin the tail. And so if the tail starts spinning one way, and I guess I can't really, well, it's the same thing, although I got to go this way. But if I were to spin it this way, then I would spin the other way. So they spin their tail one way, and their body spins the other way. And so as their whole body comes over, then they can stop spinning the tail, the body stops spinning, and then the legs are pointed down, and they fall the rest of the way down. If they don't have a tail, this one's always a little more interesting, but it can still take advantage of conservation of angular momentum. It's just a little harder to see, and the fact that they do it so quickly is amazing. If you think of this as the front half of the cat, and this is the back half of the cat. So here's my cat, quack, 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 quack. Okay, so head here and tail here. Okay, so if I take the cat and turn it over, okay, and so the back is towards the ground, and it's a bobcat, so it's got no tail on it. What happens if the cat kind of bends at the spine and moves its front part of its body this way? Well, that would be a rotation as viewed from a y-axis, right? So the back half of the body would do what? Rotate the opposite, right? So you get kind of like this effect. And so its head and its rear end get really close right there. And you got to be very flexible, obviously, for that much. But that's the advantage the cat has. The spine, very flexible and can come over like this. Then what happens with these feet over here, and the cat pushes its front feet in a rotation this way. Well, the opposite rotation is the back feet going the other way, right? And so again, total angular momentum is 0. So the cat ends up like that. And then what if the cat rotates the head back over? This has got to happen at the same time, and its rear end's got to go that way. And now its feet are down, and it drops on down. And so that extra amount of flexibility here and the multiple axes that it can rotate around always have a total angular momentum of 0, but then getting the feet in kind of a downward position. Now, another good one that, again, you guys remember from the 102 is the cheetah. Cheetah's great because that cheetah's, running, 80 miles an hour? Catching, trying to catch this antelope as it's running away. And if the antelope has half a brain, it's going to be running along going, oh no, here comes cheetah. Can't outrun it, but at the right moment, what could the antelope do? Turn, right? And so it takes a big turn and says, okay, here it comes. I'm going to turn because I'm only going, 25 miles an hour, and I can turn. Good luck, a cheetah making a turn at 80 miles an hour. It's much harder. Now, granted, it'll try. It'll put its feet into the ground. It will push. But it's going to be hard. So the cheetah has one more trick up its sleeve. What does it do? It's got that long tail that it's going to spin. And so as the cheetah is coming this way and it wants to turn that way, it rotates its tail the opposite, forcing its body then to rotate in a tighter circle. Really no different than you riding a bicycle. You do something like this. Let's see. If you were riding your bike, you would be spinning the wheel this way. And then how would you turn to the right? You would lean it. How would you go to the left? You would lean it. And so you would take advantage of conservation of angular momentum. You would realize that as you tilt the bike, as viewed from above, let's see, tilt to the right, as viewed from above, it would be going counterclockwise. So something rotates in the clockwise direction, and that's you and the bike. And so you and the bike go and turn in that other direction. And again, take advantage of that conservation of angular momentum. So one last thing. What are the units? For angular momentum. I told you, a short chapter. So what were the units for rotational inertia? Kilogram meters per second. What was the unit for angular speed? Radians per second. Remember, radians wasn't a real unit. Throw it out. So there it is. There's our units for angular momentum. It's got a kilogram, it's got a meter squared, it's got a second. And it doesn't even have a fancy name either, so you don't need to worry about any kind of fancy name. It's not a joule or a Newton or anything like that. Although we've seen so many combinations here of meter squared and seconds cubed, as it was for the watt. Just don't confuse then this unit for angular momentum with the units for linear momentum, with the units for a Newton, with the units for a joule, with the units for a torque, with the units for a watt. We've done a lot. And you're probably beginning to feel that, like we've done a lot here. And so you've got a lot of different pieces to work with. So with that in mind, now let's see if chapter 11 makes any sense. In the few minutes we have left, we'll do some examples, pick up more on Wednesday and do chapter 12, and then more examples on Monday and test on Wednesday. Perfect. And a real big example today in the lab. So I'll come over here and say, all right, let's look at number 25. 25 is a good one to get started. It's probably the most direct one we can do here in terms of rotation and angular momentum. It's exactly that. What is the angular momentum? It says this: a particle of mass 0.4 kilograms is attached to the 100 centimeter mark on a meter stick of mass 0.1 kilograms. The meter stick rotates on a horizontal frictionless table with an angular speed of 4 radians per second. Calculate the angular momentum of the system when the meter stick pivots about an axis that is A, perpendicular to the table at the 50 centimeter mark, and then B, perpendicular to the table at the 0 centimeter mark. Okay? So again, same as before, read it all the way through, get a good gist of what's going on here. It says there's some kind of meter stick, okay, so there's a meter stick lying on a table that is frictionless. So take the whiteboard as being the table, you're up in the ceiling looking down on it. There's my meter stick. The meter stick obviously has one end labeled as 0, the other end as labeled 100, the middle as labeled as 50. And what they say is there is a blob of 0.4 kilograms stuck to the meter stick at the 100 centimeter mark. Watch, I'll read it again. A particle of mass 0.4 kilograms is attached to the 100 centimeter mark of the meter stick. The meter stick has a mass of 0.1 kilograms. So maybe I'll put that on here, not to forget that the meter stick itself does have mass. And so, of course, does the blob. It says the meter stick rotates around a horizontal frictionless table with an angular speed of 4 radians per second. And so I'll put a little dot here and kind of put this 4 radians per second into the picture, because that is A. A is, what is the angular momentum of this when it is rotating around its 50 centimeter mark, perpendicular to the table, at a rate of 4 radians per second. And so hopefully the first thing that goes off in your mind is the angular momentum is equal to I omega. And then hopefully the second thing that goes off in your mind is I is the total rotational inertia. And we got 2 objects. We've got the meter stick and we've got the blob. Now, of course, like any of these questions, you can't ask what is the rotational inertia unless you also say about what point. So A is about its center. So do we know the rotational inertia of a meter stick about its center? Yeah, it's what? 1/12. Okay, times its mass. So the mass is the 0.1, I'll just put it in. Times its length squared. Its length is? Yeah, 1 meter. That's why they called it a meter stick. Okay, so 1 meter. Okay. How long is a meter stick? Yeah. When was the War of 1812? How long was the 6-Day War? I know. What color is the White House? That kind of thing. All right. Although it is a harder question when you ask what color is the greenhouse. See, that's clear. It's made out of glass, right? Oh, no, okay, all right. Or what state is north of South Dakota? There's a tough one. All right, yeah, how did I get on that? All right, so there's the rotational inertia of the meter stick. And then we got the rotational inertia of the blob. Now, this is supposed to be the easiest calculation, but I've noticed in the past students could mix this one up. So how am I going to get the next part? What is the most rotational inertia of the blob?
Isn't it from the center to the
Yeah, so let's come back to chapter 10 here. The rotational inertia of anything is the mass times the distance squared to that, to that object. And so when they say a particle, when they say kind of this blob, they're saying just all the masses at that point. So they are saying just one calculation. That's why I said it's supposed to be an easy one, but sometimes students turn this into a hard piece. It's just what mass do you have? How far away is it? So how much mass do we have? Yeah, 0.4 kilograms. How far away is it? 0.5. Yeah, half a meter. And so again, it's supposed to be that simple, just, hey, that is the distance away of the blob. So the idea of just getting to the point of where you have an object and you can get the angular momentum a little more than just one object, but it's really 2. It's the meter stick and the blob together. So I got to get the total rotational inertia.
Why did you put 1 meter for the whole, just because that whole thing measures 1 meter?
Where?
Because you got the...
Here?
Yeah.
1 meter?
I thought the R would be half of it since it's just rotating.
Well, okay, yes, but that's not what we derived. When we derived, we took a meter stick or a rod and we put the axis at its center, and the whole length of the rod was L, and we added up chunks from minus L over 2 to plus L over 2. And when we were all done, we got 1/12 mL squared, L being the whole length of the rod, even though the farthest piece was only L over 2, yes, but the L came into show. And the whole reason the L is there is because that's how we added it in proportions of the L. And that's why the 1/12 is there, because we've got the halves that are squared. Okay. So in this formula, we want the whole length of the rod, not just the distance to the blob. Whereas in this one, we want the distance to the blob. Okay? And so again, it's why it's real important that all these things you understand what's behind them. Where does it come from? That whole black box engineering stuff can be so dangerous. I'm not going to worry about it. I'm going to build a pool in the second story. That's what I want. Okay. I'm not going to worry about the first story. Who cares? Does it matter? Yes. And does the foundation matter? Yes. And so all these things, where they came from, how they were worked out, does matter. It's not just the beginning part. And so it makes a big important step on what's behind it, which is why so often things are derived and worked out and not just, given to you and say, okay, just calculate. There's a lot behind it. All right, so putting in my numbers, I got 1/12 times 0.1 times 1 squared added to 0.4 times 0.5 squared, and that is a 108, and then times the 4, make about a 4 and 3 repeating, so 0.4333 repeating forever is my first example of a calculation of angular momentum. What are the units? Kilogram meters squared per second. Good. And then I'll just drop the radians. Okay? And so there is angular momentum as the part A describes, because it's rotating around the 50 centimeter mark. But then B says, well, what if instead of rotating around the 50 centimeter mark, it's rotating around the 0 centimeter mark? So maybe a new picture would look something like this, where here is the 0 mark, and I'll put a little rotation here and say, okay, it's 4 radians per second, and here's the blob out there. Okay? But the concept of the physics is the same, that I would need to calculate the angular momentum by saying it is angular momentum equals to I omega. And again, the I would be number 1 plus number 2, and I'm going to put the two objects together. And in this case, the first object is now a meter stick, so it's a meter long, but it's rotating around its end point. So what's the rotational inertia? Yeah, around its end, 1/3 ml squared. And what would now be the rotational inertia of the blob? Yeah, now the blob would be 1 meter away as it is spinning around. And so again, coming back to this idea, the rotational inertia is the sum of all the blobs. If you got just one blob, it is the mass of the blob and the distance away. And then I have my 4 radians per second. So I've got a different set of numbers here. And I've got, actually it should be 4 times bigger. Well, let's just see. 1 divided by 3 times 0.1 times 1 squared, I guess I don't need that, times 0.4 times another 1 equals times a 4, and 1.73 repeating. And again, same units, kilogram meters squared for the inertia, rotational inertia, and then per second. Now in both of these cases, all I did was the number. What direction is it? So it's the direction of the rotation. Now the reason I put that one off is the book didn't really say what direction it rotates. But I did draw a picture. So in my picture, it's rotating positive direction. So I would put a K hat. Same thing here. Positive rotation. K hat.
That's not how you got 1/3. Where did you get that from?
Oh, now I didn't derive it today, but this is the rotational inertia of a rod about its end. I got that from the parallel axis theorem. So we did derive it at its center, 1/12 ml squared, and then applying the parallel axis theorem, meaning that if you wanted to know the rotational inertia of an object at some other point other than its center, you start with its center, and then you add up how far you moved it. And so this is 1/12 ml squared, and I am going to move half the length of the rod. I am going to move from a rotation about its center to its end, so this would be L over 2 squared. So it becomes a 1/12 plus a 1/4 ml squared, which reduces to a 1/3 ml squared. So I guess the short answer is I got it from chapter 10. and chapter 10 we did this one. So I wouldn't necessarily expect you to remember that it's 1/3, but I would be able to expect you to know that the center is 1/12, and then you can apply the parallel axis theorem to get to the end point. Okay. I will tell you on the test, on the front page of the test, I will give you the rotational inertia of 3 or 4 different objects there about its center. So if this was a test question, I wouldn't expect you to have to go back and calculate the rotational inertia about its center first, then do the parallel axis theorem, then do the angular momentum. That's not the intent. It's important you know all that, but for a test, since we only have 2 hours together, that could consume a lot of time there. So for a problem like that, I would give you the rotational inertia of the rod about its center and expect you then to start with the 1/12, apply the parallel axis theorem, and get the 1/3. Or if you've already memorized the 1/3, you could use that. Because the real point of the problem is not about that, it's about calculating angular momentum. Okay? Now, there are some problems where I won't give you the rotational inertia, because that will be the problem. Calculate the rotational inertia of a, say, disk. You know, and so you got to go through and calculate a ring first and add up a bunch of rings to get a disk and say, okay, it comes out to be 1/2. Okay, but and yeah, and you definitely have to integrate on the path to get that. Okay. Well, let's try number.
Is that a really quick one?
Ooh. Debating, should I? Maybe I'll wait on 37, but give you a hint on 36. So I got that as both in my notes, to do number 37, but also to give you a hint for 36. So let me give you the hint now. I think there's enough time to give you the hint, because 36 is one on your homework assignment, but students have struggled with in the past. It starts off this way. It says that you have 2 disks, a bigger one and a smaller one. And the smaller one is moving and the bigger one is stationary. And somebody's glued that little Velcro around the outside, and so they just brush. The tip of this one, or the rim of this one, touches the rim of that one, and then they stick together. So what happens next? Any outside forces? Any outside torques? The answer to both of those is no. So is linear momentum conserved? Yes. Is angular momentum conserved? Yes. There are no outside influences. So what's going to happen probably doesn't surprise you, but now that they've stuck together, what happens? If this is the center of mass, and they're probably one of the hardest parts of the problem. Is the center of mass where the touch? The whole reason they give you a bigger one and a smaller one. Center of mass is here. What's going to happen in relationship to its center of mass? It's going to rotate its center of mass. And then what's its center of mass going to do? Isn't its center of mass going to translate? So what we're saying here is the initial momentum is equal to the final momentum, as well as the initial angular momentum is equal to the initial angular momentum. And so it is a hard problem because you have to use conservation of linear momentum and angular momentum. Both of those are true. And here's where I think it even gets harder, and maybe I better spend more time on it on Wednesday, is when you go to calculate angular momentum. Can an object going in a straight line have angular momentum? Yes, that was the whole point of me showing you, and that's the third part of the lab, to convince yourself an object going in a straight line does have angular momentum. So to say it has angular momentum, you have to say about what point. So what point? So yeah, if you're going to calculate it about its center of mass here when it's rotating, don't you need to do it here? So its center of mass is maybe right about there. And so you don't want to calculate the angular momentum along the line connecting the two, because that's not what you're going to do later on. Why would you do it before? You don't do it that. You're not going to change your axis in the problem, are you? And so you got to pick the axis to calculate the angular momentum. Well, it's a tough problem. So once you see those little subtleties, then it's an easy problem. So that's my hint for you. So more on that later. And I guess on Wednesday, maybe the lab will help more of that sink in as we do those 3 experiments.